Sorry,
Yeah, that's fine.
wait a second.
You have to click on here to re-engage.
Got it. Okay.
Yep.
Yeah. Okay. Cool. Sure this works. Cool. Yeah. Okay, so everything's set up.
Yep. You're good to go.
Great. Thank you so much.
All right, thank you.
Yeah.
I'm gonna wait like 2 more minutes. Let's try this.
Sure.
Why is that? Oh. Yeah. Oh, it's just Thursday.
I would say let's get started. It's my pleasure to come and introduce it's a pleasure to welcome you to our research seminar series. And it's my pleasure to introduce to you Dr. Katherine Sytwu. Katherine is very early in her career. She did her PhD in 2021 at Stanford. And she did before that her bachelor in physics at Rutgers University. She's currently a postdoctoral fellow at the Lawrence Berkeley National Lab in conjunction with the University of California at Berkeley. In her short career, she's already received many awards recognizing her achievement as a student and also for teaching. Including the NSF Graduate Research Fellowship. And as I mentioned, she's right now also having a postdoctoral fellowship. And she is works at the intersection of TEM and artificial intelligence, interested in nanoparticle non-equilibrium dynamics, as you can see a little bit from her talk title, for new energy conversion platform. And with that, I'm looking forward to your talk.
Great. Thank you so much, Nina. So I guess first off, can everyone hear me? I know I'm not mic'd up, but okay, everyone can hear me in the back. Great. Okay, so as Nina said, I'm Katherine Sytwu. I'm really excited to share with you today some of my research on how we can understand how nanoparticle catalysts transform and how we can control them, all using in situ TEM as our characterization method of choice. And so catalysts are incredibly useful in our society, and there's a number of examples I can pull up. But one of my favorite examples is actually that of air pollution. So here's a picture of New York City about 50 years ago in the 1970s. And you can see that actually after 40 years, the air pollution has actually gotten better. And this is actually a trend not only in New York City, but actually a trend across the United States, where you can see that these harmful emissions in carbon monoxide and volatile organic compounds, aka smog, has decreased over the years. And this is actually due to a policy decision back in 1975, in which the US government decided that all cars being sold needed to adopt these things called catalytic converters. And so what exactly are these? So I'm not exactly a car person too much, so I had to learn a bit about this. But essentially, catalytic converters are at the end of your exhaust pipe. And what they do is they convert these harmful gases into much more breathable ones. And they do so using these catalyst nanoparticles of platinum, palladium, and rhodium. And using these catalytic converters, we can actually have much more breathable air, despite the fact that we actually have many more cars on the road nowadays. And so how do these catalysts work? So for most of these catalysts, we're dealing with what we call heterogeneous catalysts, in which they're solid materials upon which molecules will essentially absorb to their surface. And through this absorption process, it'll lower the activation barrier for a chemical reaction to happen. And so importantly, what we're trying to achieve here is basically make sure that as many molecules absorb to the catalyst surface as possible, so therefore we can have much more efficient reactions. And so therefore, nanoparticles are an ideal platform for catalysis, particularly because of their extremely small size you get a large amount of surface to volume ratio. And especially in the past decade, we've invested a lot into research on nanoparticle synthesis. And so now we can create nanoparticles with extremely tailored surface properties, but whether in their faceting or in their chemical composition right at the surface. And so when we create these nanoparticle catalysts, what are we interested in learning about them? The primary thing we want to know is, well, what did we create? What is its structure? What are its structural properties? And the reason why we care about this is because we found that over the years, the chemical function is highly correlated with structure. So for instance, here's one example of a seminal paper from back in 2004, where they showed for carbon monoxide oxidation, you can have these gold nanoparticles. Actually, you can just have gold in general. And it's really inert to this process. You can put it under this chemical reaction and it doesn't help at all. In fact, even if as you create 30 nanometer nanoparticles, nothing happens. However, once you start making the nanoparticles smaller and smaller, let's say on the order of 2 nanometers in diameter, you actually see this giant jump in activity. And so these small nanoparticles are actually much more active than these larger ones, even when taking in consideration the difference in surface area. Similarly, we can also see differences when we change the shape of our nanoparticle, aka the surface faceting, and so the order of the atoms that the molecule sees. So you can see in this example for formic acid oxidation, as you change the palladium catalyst nanoparticle shape, you can actually get differences in activity as well. And so with all of this, we now know that structure is really important. However, when you actually put these materials under the conditions necessary for a chemical reaction, you actually learn that structure can change. So here's a video of a nanoparticle catalyst, and you can see that its morphology and its structure is changing as it interacts with the gas environment. And in general, when we have these catalysts, they can change in a multitude of different ways. So for example, we can have that shape change. We can have phase changes as the gas molecules intercalate into the nanoparticle, or perhaps induce some sort of other phase transformation happen. They can sinter and coalesce, basically go from really small nanoparticles to much larger aggregations, where you can actually have chemical changes in the alloying or segregation of the chemical elements themselves. And so because we also know that structure is highly correlated with chemical function, and now we know that structure changes, well, that means that chemical function can also change during an experiment. So here's an example that I really like, showing sort of the chemical activity of thousands of catalysts under carbon dioxide reduction, I believe. Oh, sorry, carbon monoxide oxidation. And you can see from these TM images that these dips and changes in chemical activity are actually correlated with changes in the nanoparticle structure. Specifically in this instance, just the formation of a sharp edge. So just this small difference can actually have humongous impact in the large-scale chemical activity of these structures, despite, again, such a nanoscopic atomic change. And so if therefore, structure isn't necessarily the only thing that we care about, and we know that structure changes, our question is now no longer, what structure do I have in my nanoparticle catalyst? But instead, how do my nanoparticles transform when I put them under reactions? Once I understand how do they transform, how can I control that transformation? And again, this doesn't happen over 1 nanoparticle or 2 nanoparticles, but over thousands and millions of nanoparticles. So how can I know the probability distribution and general behavior with statistical certainty? And today I'm excited to share with you some of my research trying to answer these questions. First, focusing on model systems, trying to understand how exactly structure influences dynamics in palladium hydride nanoparticle systems. Then introducing light as a means to control these transformations down at the nanoscale so that we can dictate what behavior we see. And then finally, by using machine learning to really expand this from a single particle analysis technique to a multi-particle ensemble analysis, where we can actually start to understand how behavior changes at the larger scale. So let's start off with structure and understanding dynamics. So the model system I'm going to talk about today is that of palladium hydride and its phase transformation. And this is a really important phase transformation in hydrogenation reactions with palladium catalysts. So as an example here, we can see here that during carbon dioxide reduction, as the palladium catalyst changes from basically palladium on its own to a palladium hydride, you can actually get a dip in activity. And so generally what chemists are trying to do in these reactions is actually prevent the formation of palladium hydride. Sometimes though it can be beneficial, but regardless, this transformation is extremely influential in these reactions themselves. So what exactly is this phase transition? So palladium hydride consists of two phases. One we'll call the alpha phase or hydrogen 4 phase. You can think of this as just palladium on its own. Then you can change the hydrogen pressure of the system or the temperature and induce a phase change into the beta phase or hydrogen rich phase, in which the hydrogen ion basically intercalate into the palladium lattice. And this expands the lattice. It also changes its electronic properties. But essentially you have these two phases and then you can sort of, switch between them reversibly as well by changing the pressure and temperature. So how does this microscopically happen? So first, you have hydrogen splitting and absorption at the surface of the palladium material. The hydrogen ions then intercalate into the subsurface or first 1 to 2 layers of the material itself. And then finally, you see diffusion into the bulk. And so you see this macroscopic phase change. And specifically, since this is a surface catalyzed process, this is induced by something that's happening at the surface, it then becomes a natural question of, well, what happens if I change the surface of my nanoparticle? How does that change the kinetics? How does that change the dynamics of this phase transition itself? So to do so, we synthesize nanoparticles of 2 different surface facetings. So first, we synthesize palladium cubes, which are completely surrounded by 100 facets. And then we also synthesize palladium octahedra of the same size, which are completely surrounded by 111 facets. And what I find really interesting about this system is that they're complete opposites of one another. The corners of the cubes point in the 111 direction, and the corners of the octahedra point in the 100 direction. So to verify that we've indeed synthesized what we said we would make, we have SEM images showing that we have cubes and octahedra. We can take TEM images showing that, yes, indeed, we have a cube. And here we can see an octahedra, and because of the way they fall, you can actually sort of imagine, like, I don't see this diamond shape, but actually you do if you think of it as basically lying on its face and you see this specific projection. And then using single particle electron diffraction, we can again verify that we're at the facet direction that we said we synthesized as well. So then once we synthesize these nanoparticles, how are we going to detect the phase transition itself? So as I mentioned before, I use a transmission electron microscopy, specifically in situ transmission electron microscopy, to study these processes. So in transmission electron microscopy, you're using a highly accelerated electron beam, and because it's electrons, you have a much smaller wavelength, and so you can actually image things at the atomic scale. But in my PhD, we were really lucky, and we had access to a microscope with called an environmental TM, where we can actually flow gas into the microscope itself. So we can really create that chemical environment. And then on top of that, we have these extremely advanced sample holders, which allow us to introduce other in situ stimuli, such as heating, biasing, cooling, light, etc., so that we can actually not only just image things at the nanoscale, but we can actually do experiments at the nanoscale. And so not using TM as just an imaging platform, but rather a nanoscale experimental platform itself. And so on top of that, we not only can image, but we can also do spectroscopy. And so we can get not just structural information, but also electronic and functional information as well. So going back then to our palladium system, how exactly are we going to investigate the dynamics themselves? So we can do so 2 ways, especially at the single particle level. So first is on the single particle level, we can utilize the structural change in our phase transition and capture that using electron diffraction. So as I mentioned before, when we're in alpha phase, we'll have a certain single particle electron diffraction. And as it goes into the beta phase, it'll expand, meaning that our diffraction pattern will shrink. And then we can capture that about 3.5% change by just analyzing our diffraction pattern there. We can also not only get single particle resolution, but also sub-nanoparticle resolution by condensing our electron beam into a scanning probe. And then instead of looking at diffraction, what we can do is we can actually look at spectroscopy. And so here, what I'm showing is this electron energy loss spectroscopy. So basically looking at the energy that the electron has lost as it passes through a specific nanometer point in the material. And you can see that when we look at essentially the plasmon resonance of the material itself, or essentially how the electrons react to the electron beam, we can see that in the alpha phase, we have a peak at around 80 eV, and then in the beta phase, this shifts down to about 2 electron volts to 6 eV. So by using electron spectroscopy, we can know with nanometer resolution what phase the nanoparticle is in at that specific point. And so with these techniques, we now go and actually try and measure it. So first, before you go into the dynamics, the first thing you always need to do is understand how does the system behave at equilibrium. So we can take isotherms in our microscope. Essentially, we set a temperature and pressure, and then we measure what phase the particle is in. And in general, what we find is that these single crystal nanoparticles do not support coexisting phases, meaning that if I set the temperature and pressure to a certain setting, I will only either see it in alpha phase or all in beta phase. And that's what we see here for both the cubes and the octahedra. So when we want to see the dynamics, what we do is we set the temperature and pressure to just so it's slightly below where it'll transform into the beta phase, and then we start imaging. Okay. So here I'm showing movies of exactly what we see. So here what I'm showing are these scanning TM images where we're master scanning the probe, and we're basically looking at the nanoparticles as they transform. And so what you might see is that every so often I'm pausing the movie, and then you see this little mouse cursor moving around. And that's because off screen what we have is actually that electron spectroscopy allowing us to verify when I put the beam or the mouse cursor over a certain area, I can then verify what phase that particle is in. And specifically, what we see in these annular dark field images is sort of this change in intensity. And that's due to what we see induced strain due to the new phase coming in, changing sort of the dark field image that we see. And so this went a little fast. And so here I can show screenshots of exactly what we see, which is we see that the phase transition happens from the corners of both of these nanoparticle systems and then before progressing through. So specifically, we see this corner nucleation and growth type of dynamics. So in cubes, we see that the beta phase comes in through one of the corners before creating a phase front and then pushing through. And in the octahedra, we see the same exact thing. We see that the new beta phase nucleates at one of the corners before creating a phase front and then pushing through. In the octahedra views, the interface is not aligned, it's not parallel with the electron beam. You actually see that the interface is this rectangle almost that sort of grows. So you can think of it as a pyramid growing in size. And so specifically, again, we'll reiterate is that we see that this is a nucleation and growth process that is facilitated by the corners of the particle. This is actually not a surface process. We don't see changes through the surface, but in fact, it's the corners of these nanoparticles that dictate the dynamics that we see. But with TEM, we can not only just get, this qualitative information about the dynamics, but we can actually get quantitative information as well. By tracking the phase transition over time in individual nanoparticles, we can actually get a sense as to the rate limiting behavior. So for instance, if we track the phase front in both cubes and octahedra, we find that they follow a linear sort of movement. And so also if you quantify this, this gives us times that are actually quite slow, much slower than what you would expect for a diffusion limited process. And so the fact that we see this linear-like behavior coupled with the time scales that we see suggests that we do not have a diffusion limited behavior. And so then what exactly is causing this? What exactly is causing this both corner nucleation behavior and its slowness? And so we hypothesized 3 things. So first, we hypothesized it's still limited by something at the surface, absorption of hydrogen splitting. And indeed, what people have shown a couple years later is by changing the ligands of your nanoparticle system, you can actually then completely change the rate. And so that sort of supports this idea that this is a surface limited process. Another hypothesis was that this is actually due to the corners themselves, the corners and the edges. If you have more corners, you should also show faster hydrogenation kinetics. And indeed, that was also confirmed about later, where they created these nanoparticles with much more corners than edges, and they also showed much faster kinetics as well. And then finally, we had this idea that it's actually due to strain formation. And this one was a little bit harder to verify. But I'm happy to talk about it if anyone's interested, but we actually have later results that sort of suggest that strain and defect actually play a huge role in the kinetics and propagation of this phase front. And so to sort of summarize this section, what we learned is that in these palladium hydride nanoparticles, the dynamics are highly influenced by nanoparticle structure, specifically the corners. If I have a nanoparticle structure, I know that my phase transitions are going to be dictated by the corners themselves. So again, we've shown that we nucleate the new phase at the nanoparticle corners, and that this phase transition itself, because it propagates at a linear rate, it's not limited by a diffusion process. Okay. So great, we now understand how these material systems evolve. And so how can we then control it? Other than just changing the nanoparticle shape itself by creating new corners, how can I potentially see new behavior without actually having to change my material system itself? And so I had this idea that we could do so. Well, first off, I should say, we need a way to really target, at the sub-nanoparticle level, right? We see that the corners are important. So how can we target areas of the nanoparticle that are not its corners? Okay, and so we think back to all the control knobs we have in our experiment. We have two of them, right? We have the temperature of the system and we have the gas environment. But notably, both of them are much larger than the nanoparticle system itself. If I change one of them, I'm going to change it for the entire system. I can't target specific atomic sites on the catalyst or material. And so instead, I had this idea that what if we can use light? So light, if you actually think about its length scale, is actually quite large with respect to nanomaterials. For visible light, it's 400 to 800 nanometers. And our nanoparticles, again, are much smaller. We're dealing with anywhere from 10 to 100 nanometers. So it's actually much bigger, but there is a way that we can actually make light much smaller, and it's through a phenomenon called a local surface Poisson resonance. So local surface Poisson resonances, which I'll just refer to as plasmonics for the rest of this talk, is this collective oscillation of conduction electrons. And essentially, there's two really interesting phenomena. So essentially, when you have light hitting a metal with a lot of conduction electrons, essentially the metal nanoparticle acts as a cavity in which those electrons can resonate. And this leads to two really interesting phenomena. One is that you can actually sort of enhance the electromagnetic field at a sub-wavelength regime, creating what we call these electromagnetic hotspots. So I will say it's actually a huge misnomer in the field. We don't know for sure that these spots are actually thermally hotter than others. But what we do know is that these will create extremely confined and enhanced electromagnetic fields, as seen here in this electron energy loss spectroscopy map of the silver nanoprism, and you can see that the electromagnetic field is highly confined to these nanoparticle corners. Another really interesting phenomenon that we see is that these plasmons can actually increase chemical activity when used as catalysts. So specifically in a number of different experiments, what people have shown is if you have these plasmonic nanoparticles and you shine light and excite the plasmon resonance, you can actually see increased chemical activity. But even more interestingly, you can actually see increased product selectivity. You can actually change the reaction pathway, and in a way that's different than if you just thermally heated up the nanoparticle itself. And so I was wondering, with these two things, the fact that you can have extremely high confinement of electromagnetic field and highly and drive chemistry, can we then use plasmons to drive nanoscale local chemistry? And so we weren't the only ones with this idea. This has been what a lot of people have been trying to do, but it turns out this is a huge characterization challenge. But people have come up with a number of ways to sort of overcome this. So this is one example. So here they have a plasmonic bow tie structure where the electromagnetic or plasmonic hotspot is right in the middle. And so they actually use these silver nanoparticle markers to basically mark out where does a chemical reaction happen. And they found that most of the markers happen to be exactly at that electromagnetic hotspot itself. However, in this experiment and in many others like it, these plasmonic hotspots also happen to coincide with where the catalyst itself is most active without any enhancement itself. So nanoparticle catalysts also have uneven chemical activity across their surface, and in generally corners happen to be usually the most active sites because of their under coordination. And so I have this question of, well, what if you wanted to induce activity at a site that wasn't usually active? Can we use these plasmonic hotspots to actually induce new dynamics, to induce activity at sites that normally do not want to have any activity themselves. And so when I was thinking back to my palladium system, we then run into another problem, which is that palladium is not very plasmonic. And so to illustrate my point here, I'm plotting out the extinction cross-section for about a 20 nanometer nanoparticle made out of different materials. So here we have those same, catalytic materials that I showed for the catalytic converter. And you can see that for these materials, our extinction cross-section is quite low, aka that means it doesn't interact with light that much. However, if I change up my material to what we call a plasmonic material, you actually get much higher extinction cross-sections. We actually have this high interaction with light. And so therefore we can, and it turns out we can actually make palladium and all these catalytic materials much more plasmonically active by combining them in a bimetallic geometry, a number of which I'm showing here. So one is an antenna reactor where you're optically coupling the two materials. You can have coarse shell where you have an interface, or you can have alloy particles where you have a lot of atomic interaction as well. So today what I'm going to actually focus on is antenna reactor. But one interesting thing I think of is really how can we extend this to coarse shell and alloy particles, which are much more scalable. But today, just antenna reactors. Okay, great. So then how do we design a system? So then I designed a system where we essentially have this antenna reactor system where we have a gold plasmonic antenna whose job is to basically collect all the light and funnel it to this palladium nanorod reactor, which is this cross on top. And specifically, this design is such that the electromagnetic hotspot is located far away from the reactive sites of the palladium nanorod. So here I'm showing the simulated electromagnetic response of one of these systems. So here you have a cross-sectional view of the palladium nanorod and the gold, and there's actually a small little gap in between them. And you can see from our simulations, the plasmonic enhancement or electromagnetic enhancement, is located right at the middle of the palladium nanorod, right at the gap of the two, and away from the active sites, which we believe will be the tip of the nanorod. Okay, great. So then what exactly do we do? We then create this system using a combination of e-beam lithography as well as colloidal nanoparticle synthesis. And then we stick this into our in situ TM, except now with a optically coupled folder. We actually use a cathodoluminescence folder, which allows us to couple in a pulse laser to then excite the plasmon resonance of our gold nanostructure. And when we excite that plasmon resonance, what we hope to do is actually push the particle from the hydrogenated beta phase into the alpha phase. And what we were curious about is how does this transformation differ now that we have this sculpted electromagnetic response at the nanoscale? So specifically, this is what one of the fabricated structures look like. So you see the fabricated gold nanobar and the palladium nanorod crossed on top. So then how do we image this? So one thing I sort of glossed over in the previous section is the temporal resolution that we had with scanning TEM. So there we had a temporal resolution about 2 seconds per frame. That is way too slow to capture light-induced behavior, which happens much faster. And so we needed a way to actually image these dynamics with both spatial, temporal, and chemical resolution. And so we do so using dark field imaging itself. So I'll walk you through exactly how we do so. So this is a single particle palladium nanorod diffraction pattern where you can see all the diffraction spots. And so if you place an objective aperture over one of the spots, what we're doing is we're highlighting a single crystallite of our polycrystalline nanorod. So then when we take the dark field image, we can actually see just the palladium nanorod itself. And specifically, if I'm in the beta phase and I place my objective aperture just carefully enough, that means when I go from the beta phase to the alpha phase, or I dehydrogenate my particle, the lattice will contract, meaning my diffraction pattern will expand, meaning that my diffraction point will be pushed outside of the objective aperture, meaning that there's no signal here, and so therefore I see nothing. And so therefore we can combine essentially the high temporal response with TM mode. We have extremely good spatial resolution, extremely good temporal resolution, as well as the fact of whether or not I see signal gives me an indication of the chemical nature of the system, namely, is it in beta phase or is it in alpha phase? And so with this imaging technique, we then move on to actually investigating the dynamics. So first we look at without illumination, what happens with just palladium nanoparticles on their own? Well, we know from the previous section that it's probably going to happen at the corners. That's exactly what we see here. So we see that we lose the phase transition again, nucleates from the corners, basically nucleating the alpha phase from one tip. Then we see a second nucleation event at the other tip before fully transforming from the beta to the alpha phase. Now, what happens when we introduce light and plasmon excitation? So now I'm going to show a movie where upon the start of the movie, we're turning on the laser exactly on resonance with the plasmon response. So here, we can actually see that we lose signal right there, right from the middle of the nanoparticle itself, showing that we're actually seeing a completely different dynamic. But interestingly enough, when we turn off the laser, we turn off the stimuli response, we see that signal starts to come back, meaning that we're indeed using light to sort of push the nanoparticle outside of where it's thermodynamically favorable in the beta phase into the alpha phase, and we've completely changed the dynamic. And so if we do this a number of times, we actually see a number of different dynamics. So two dynamics, I should say. So one is this middle nucleation, where it actually nucleates, its nucleation point is basically near the electromagnetic hotspot. And the other is actually what I call single tip nucleation, where we just see one nucleation site at the tips without a second one at the other end. So uncreatively, I call these double tip, single tip, and middle nucleation. So if you do this over a number of particles, we actually start to get some statistics. So in the dark or without any plasmon excitation, we see that almost all of the particles show this two-tip nucleation process. However, once I have this plasmon excitation, I actually start to see completely new dynamics. Actually, most of them do not show the same dynamics as that under dark. And then the next thing we need to do is verify that this is actually due to the plasmon. It's not just a light-induced process, but actually due to this interesting light-matter coupling. And so we can do that by actually sweeping our illumination wavelength. So recalling again that we have an experimental platform where we can now understand what's happening. And so here, every single point is a specific illumination and trying to understand what dynamics are happening. And what you can see is as we sweep the illumination wavelength and power, we actually see different behavior. Specifically, we only see this middle nucleation when we're around 600 to 650 nanometers. And this actually corresponds with the plasmon resonance of this specific single nanoparticle system, where here we're showing an electron energy loss map of the plasmon resonance. So again, we're using electron energy loss spectroscopy to measure the plasmonic response. We see that it peaks around 2 eV and that it is indeed centered such that all the enhancement is far away from the nanoparticles. Okay. And so from this, what can we learn from this information then? We've done this great experiment, but what can we actually learn? So one huge question in the field is when I have this plasmon-driven chemistry, what is actually causing it? And there's three main byproducts. There's electromagnetic radiation, there's hot carriers, and there's also heating. And notably, all three of them will always happen. It's just a matter of which one is actually important. And so specifically, these three will have different spatial profiles at the nanoscale. Specifically, radiation and hot carriers will only give you local excitation, meaning that you will only ever see this middle nucleation-like behavior, while heating can have both local and non-local effects, meaning that you can see all sorts of behavior on its own. So what we know then is that that single tip nucleation behavior that we see can only be caused by plasmonic heating. And then we end up doing additional experiments with combining molecular dynamic simulations as well as completely changing the hydrogen pressure of our system. And we actually think that radiation and hot carriers are leading to some of the really interesting middle nucleation behavior. So to summarize this section, what we did is that we designed a system that separates out the electromagnetic hotspots from the reactive sites and showed completely new dynamics once we have this plasmon excitation. So notably, the takeaway here is that by introducing light, by introducing optical sculpting, the optical excitation at the nanoscale, we can actually see new dynamics that are not completely determined by nanoparticle structure. And specifically, not only that, but using in situ TEM, we have this interesting experimental platform where we can do experiments at the nanoscale and really not just do imaging, but experimentation. But one thing I learned from all of this, I'm doing single particle studies. I'm getting a lot of information about how specific properties of a single nanoparticle corresponds to its behavior. But as I mentioned before, catalysis doesn't happen over one particle. It happens over thousands. And so we need some way to scale up. And it turns out that you don't need to change your technique. You can actually stick with in situ TEM. The main thing is you just have to widen your field of view. So here you can see two wider field view TEM images where we can look at, instead of one particle, but thousands of particles, and we can get statistics over its nanoparticle diameter. Or we can look at movies in situ movies over many particles. So let me see if I can replay this. Yeah, so you can see the diffusion of these gold nanoprisms in a liquid cell. And so you can see how they move around and actually get an idea at the single particle level of its diffusion behavior and the distributions of those behaviors. But not only what we care about are these quantitative measures, but what we get are these images. And so in order to go from one to the other, we actually need one more piece of information, and that's actually image analysis, or these segmentation maps where we identified where in this image is this particle. And thankfully, the computer vision community has come up with a number of routines, such as it's very easy once you have the segmentation map to get statistics, to do analysis on single nanoparticles. But the difficult question then is not how do I get this quantification, but it's actually how do I go from image to a segmentation map or quantitative information. And so currently there are a number of ways that you can do this. However, one of the most promising ways is through machine learning or neural networks. And the reason is because these images are not very straightforward to analytically analyze. So to give you an example, here's a high resolution TM image, and this is the typical imaging mode for most in situ experiments. And so here what we're looking at are these 2.2 nanometer gold nanoparticles. And I can ask you, okay, where are the nanoparticles in this and how did you find them? So for me, the most telling aspect is actually these lattice fringes. We know that these nanoparticles are crystalline, and so we know that we will see lattice fringes corresponding to a gold crystalline nanoparticle whenever I see this periodic behavior. However, that's only true part of the time. Sometimes the nanoparticles are off zone axis. So instead of seeing this texture problem, you actually see a dip in contrast, as seen in this nanoparticle here, where I know this is a gold nanoparticle, but I don't see any lattice fringes on their own. And then sometimes I have some nanoparticles where part of the grain is on zone axis and then part of it is off. And so, for example, here, half of the nanoparticle has a lattice fringe, but half of it doesn't. So how do you create an analytical method that can capture all of these potential outcomes? Turns out it's pretty difficult. And so one of the most obvious ways to do, or I shouldn't say obvious, but one of the easier way to do it is by training a neural network. And so people have shown that you can train neural networks to detect nanoparticles in these high-res TM images. So for example, here's an actually pretty difficult image of these cadmium selenide quantum dots. They're also about 2 nanometers, and it's the question of where are they in this image? So with analytical techniques like Fourier filtering, it's actually pretty difficult to find them, but a neural network can find them quite well. And so how exactly, again, do these methods work? So neural network performance really revolves around two things. One is training data, in which you take data in which it's very similar to what you want to analyze, and as well as labels as to what you want your algorithm to learn. And then you feed it to a neural network architecture, and you basically show it in examples, you basically update the weights of the network, and eventually you get a trained neural network. You feed it new data, it gives you an output, and then you're good, all settled. And it sounds really easy, and it sort of is a bit straightforward, but it turns out in practice, it's not as easy. What you end up is a lot of problems. There's a lot of questions on what exactly is happening. And a lot of the reason why it's really difficult to get this working in practice is because if we think back to more first principles, how have these algorithms been developed? They've been developed with much more different goals than what we want to do. So to give an example, I think about what is the difference between computer vision problems and scientific microscopy problems. And so one example is like the data sets we work with are very different. So for example, in computer vision, they have these very large data sets that they're taking years to get, but also through scraping the web, and that they're relatively cheap to label. And I don't mean cheap as in just financially, but also in finding experts who know what's going on. So for example, I can probably find anyone off the street who can tell me this is a dog and this is a coffee making machine. However, it's actually much more difficult to find people that can tell me, what is it that I'm seeing in these microscopy data sets? And on top of that, they can be expensive to acquire and they're usually much smaller in size. Similarly, if you think about the data structures themselves, they're very different. So in computer vision, you work with small digital images. In microscopy, we've invested thousands, millions of dollars into these high-end CCD cameras. And then we have to convert them into images. We have to deal with data that is just fundamentally different. And then on top of that, even the motivations are slightly different. If you look at computer vision, you're trying to get the best performance possible, evaluated on some benchmark data sets. But the most important thing is that you do extremely well. You create algorithms that work. In microscopy, I will argue that I will take a slightly less performing method if I can understand how it works. Because I don't care if my method tells me that this is a nanoparticle. I want to make sure that it knows that it's a nanoparticle because of the right reason. If it tells me something because of the wrong reasons, then that's not actually a method that works. Because what we care about in microscopy and in characterization is this idea of generalization. We're generally looking at new things, and so we want to make sure and validate that our new predictions are correct. And because of this slight difference in philosophy and in what is important, this means we need to rethink a bit about how we retrain and how we develop these machine learning algorithms as well. So in my postdoc, what I've really focused on is really trying to understand how does our training protocols and how we treat data have to differ when we have this TM data or scientific data? And specifically, instead of treating neural networks as a black box, really try and uncover what is important, what do we need to do, and why do we need to do it? And so specifically, I focused in on this example class of nanoparticle segmentation, where again, we're taking a high-res TM image, and then we're trying to identify for every single pixel in this image, is it part of a nanoparticle or is it part of the background or just not a nanoparticle? And so when we have a prediction, we can then evaluate how well the prediction does by using something called a dice score, which quantifies a similarity between these two images, between 0 and 1, with 1 being very good. So then great. Okay, so what are some of the questions I decided to research? So first off, if let's say you're like, okay, neural networks are great, I want to use them. What's the first thing you need to figure out? Well, the first thing you need to figure out is, well, what network architecture do I use? There's a complete zoo of architectures that have all been proposed and they all work really well. And then the question is, well, how do I know which one is going to suit my data over the other? And so what I wanted to understand is, okay, so then what are some of the descriptors of network architectures? Well, there's two of them that I thought were really helpful. One is complexity, and the way I like to think of this is, in the order of the number of trainable parameters. So you can also think of this in the idea of curve fitting, right? So let's say I had a bunch of dots and I had to fit a curve. A relatively simple curve would be a linear fit, and that'd be 3 trainable parameters. Actually, no, 2, right? Your slope and your intercept. But you have a much more complex function, let's say like a 4th order polynomial. That's a much more complex a network or architecture. The second is that of receptive field, and this was defined as the area of an input image that contributes to your decision point at the end. And so this was hypothesized about a year or so ago to actually be really important in these TM images. And in fact, many people have shown that this receptive field is quite important whenever you translate into applying these algorithms into new data. And so, but the real difficulty here is that receptive field and complexity are often quite linked up together. It's if you just take a random architecture, they will usually have completely different, there's complexity and receptive fields. And when you try to change one, you often end up changing the other. So what I wanted to understand is which one out of these two is actually important? Because when we understand that, then we know how to design better architectures and what is actually important. Because one other thing I'll mention is complexity or the number of trainable parameters is always going to give you a lower limit as to how much data you need. It's known that if you make a more complex network, your network is going to perform better. But if you create a very complex network, you're going to need a lot of data. And in microscopy, where we don't have a lot of data, we want to know how important then is complexity. So what I did is I trained multiple network architectures and systematically changed only the receptive field or complexity. So here what I'm showing is essentially neural network performance on these 5 nanometer gold nanoparticle images. And so for every single point here, what we've done is we've trained an architecture with a specific receptive field and complexity shown in the color. And then what I did is for every new architecture, basically they see the same exact images. And so as we travel across this line, the only difference is the receptive field of the network. And you can see that performance actually starts to increase and then plateaus. Then what happens if I increase the complexity of this network? So I see the same exact behavior, which is that as I increase the receptive field, performance goes up and it again plateaus. And again, if I increase this complexity even more, I basically see that along a certain receptive field amount, I get this plateauing of behavior. And I think there's two takeaways here. So one is, right, like as we increase receptive field, we basically get better performance up to a certain amount. But interestingly enough, if you compare the complexity of these two networks, in this dark green, we have a much more complex network or many more trainable parameters. And it happens to do exactly as well as a much simpler network with the same exact receptive field, but much fewer parameters. And this sort of tells us that, receptive field is probably the more important structure. You need a certain amount of complexity, but more important is this receptive field value. And so we wanted to know, okay, well, what exactly why is this the case? And so we repeat this for not just our 5 nanometer nanoparticle data set, but also what happens if you have different data? Let's say 2 nanometer nanoparticles, where the nanoparticle is smaller, but it's also much less contrast, and you see the same receptive field behavior. Similarly, if I increase the nanoparticle size, have much larger nanoparticles, or even go into a completely different type of TM imaging, where standard TM imaging, where I don't have lattice fringes, and then you can see in these high contrast modes, we actually don't see any receptive field dependence. And so we hypothesize that actually this receptive field dependence is inversely correlated with nanoparticle contrast, which also makes sense if you think about it, right? Like if I have a low contrast nanoparticle, I need a lot of contextual information to correctly make a decision. But if it's a relatively easy image, I don't need that much information to know for sure that it's a nanoparticle. Okay, so this ends up being a really nice systematic view of how network architecture influences our performance. But as I mentioned before, one really important part of microscopy and in situ TM is that I need performance to be consistent as my sample is undergoing a change, in my in situ experiment. And so we really need these workflows that generalize well out. So I was curious, can we apply the same systematic analysis maybe to the data side? Understand what is the data over which our networks will still perform well? And so specifically, how does the training data affect the generalizability of our network? And so here, what I ended up doing is basically collecting all of these images with very controlled metadata. So here we have 5 nanometer gold nanoparticles taken out of specific microscope conditions. So what I did is I collected many more data sets where all I changed is just one parameter. So specifically, maybe just changing the nanoparticle size. So instead of 5 nanometer nanoparticles, I have 10 nanometer nanoparticles. Maybe just changing the nanoparticle material. So instead of gold, I have silver, or even changing the electron dosage so that I have a much different signal to noise level. And then what we are interested in is, how do networks generalize out? If I have an in situ video where conditions are constantly changing, around how long can I actually trust that my predictions are correct? And also, how many images do I actually need to correctly train my network? And so this is still a bit ongoing work, but some of our preliminary results suggest that we do see generalization across nanoparticle size. Nanoparticle material gets a little dicey. You really need to understand both the structure, but also it turns out generalization is not a two-way phenomenon. It's very much a one-way phenomenon. So one type of condition might generalize to one, but not to the other. And with dosage, we actually see that this is something that you need to be really consistent with. And so this sort of suggests then that, neural networks are probably going to be very good for in situ data sets where microscope conditions are generally very constant. The other thing we found is actually that data processing plays a huge role in generalizability. So specifically, how do you take data from our CCD camera and convert it into a training set for machine learning? And turns out you need to do a number of pre-processing steps, and the choices of what you decide, how you decide to rescale, how you decide to take out background ends up being extremely important in making sure that you're actually basically testing and having a network that works across multiple microscope sessions rather than a network that really works very well in proof of concept for your one data set, but does not work for anyone else's data. So to sort of summarize this section, what I've shown is that we have these extremely powerful machine learning tools and neural networks, but we really need to better understand them in our domain of interest. So specifically, I showed an example of how we can analyze how neural network architecture affects our performance in these high-res TM images, but also some of our work in really figuring out that, these data-driven algorithms need closer examination of the data if we need to deploy them successfully beyond just proof of concept. And it sounds, when you look at it, it's like, oh yeah, data-driven algorithms, you have to care about the data. But in fact, we really need to understand how exactly is the data we feed in and how that affects our trends. So with that, to summarize my talk today, I've shown you that structure really dictates dynamics in these nanoparticle systems. And by introducing light, we can really induce new behavior. And then by introducing concepts from computer vision and computer science, we can really take this technique from a single particle analysis to an ensemble scale analysis. So then what exactly can we do with this information, or what's next? So with these, using nanophotonics to control behavior, we can think about creating like multiplex catalysis, where we're essentially using light to induce reactions at potentially different parts of the nanoparticle, and really having, instead of thinking about our catalyst as a single structure with one sort of functionality, we can think about exciting different sorts of functionalities with spatial resolution. And this has a lot of applications in nanoparticle synthesis and creating designer nanoparticle structures, where instead of dictating where things are happening with ligands, we can dictate where it happens with light. Another possibility is that once we have these algorithms that really work in analyzing at scale, we can actually start to analyze these movies and quantify these dynamics, and really now, take advantage of some of the advances in theory, which have predicted this probability distribution of nanoparticle structures, and start to correlate our experimental observations with the theoretical calculations, with some sort of more ensemble analysis rather than a single event in time. And so with that, I'd like to thank all of my collaborators. So most of the work with palladium particles was all done at Stanford, working with my PhD advisor, Jennifer Dione, and the machine learning work was done at UC Berkeley, as well as Berkeley National Lab at the Molecular Foundry with my postdoc advisor, Professor Mary Scott. Just need to acknowledge all of my funding and research sources over the years, and I'm happy to take any questions. Yeah.
Take care of you and the discussion, and thank you for your talk.
Any question for Dr. Sytwu?
Work with change analysis and I've always noticed that the endpoints of the data set tend to have issues with that analysis. Is it due to the algorithm of your neural network having the understanding like the edge of the nanoparticle versus the edge of the image that dictates that parameter, or is it more complicated?
It's so I'll answer actually the two parts of your question. So maybe the answer to that is actually no. So it's a little bit different. So let me just show you a diagram, actually, if I can pull it up. So with these receptive fields, what happens is that when you define a specific architecture, let me see if I have a good schematic for this. When you define a specific architecture, you have your input image. So, okay, here. Okay. So when you define a specific architecture, what we are working with are what we call convolutional neural networks, in which we're basically saying we have an input of an image, and we only take a portion of it and we sort of propagate it through, and eventually it creates a decision point at the end. And so if you back propagate and calculate how much of the image input is actually used to make that decision, it's not always the entire. If you don't design your algorithm or your network architecture correctly, you're not actually using the full image. You're not inputting the whole image because you have this convolving filter. So it's actually much smaller. And so what we did is that, so here you can see in this schematic. So here we have essentially the same network, but different receptive fields. So if I design it in one way, essentially, when I make a decision point at this middle pixel, it's only using the information here. And then if I create a different architecture, it's only using information in this yellow box and so forth. Yeah, I hope that sort of clarifies it a bit more. It's sort of in the algorithm. Yeah.
Any other questions?
I was just wondering, when you're doing the fabrication of your antenna reactor system, photography, and then you just put the reactors down randomly and look for one that's orthogonal, because you keep going.
Yeah, let me show you actually some pictures from the actual thing. So yeah, we essentially fabricate them. We fabricate the gold, we then put down a silicon dioxide layer. And so what the silicon dioxide does is that it makes Sytwu means that we can control the hydrophilicity of the entire surface. So then when we drop past nanoparticles, we can actually make sure that they're oriented randomly. And so you can see in this wide field view image, first off, the nanorod synthesis isn't synthetically pure, right? I have a bunch of nanocubes. And so you have both nanocubes and these nanorods, and you just sort of randomly get orientations. And so one thing we actually have to do before every experiment is to sort of screen the sample and find where exactly do we have.
And your cartoons and the examples, like you were going for orthogonal, did you look at the angle dependence at all?
Yeah, so we actually have a couple with angle dependence, and it doesn't seem to matter. And that's because the optical phenomenon is actually not related to the angle at which the Palladium rod is at, because what we're actually exciting is the transverse mode of this gold nanobar. And so what the Palladium rod is actually doing, all it's doing is that it's confining that electromagnetic enhancement to the gap rather than just the size of the nanobar. So regardless of if the Palladium nanorod is at an angle, it's still providing that confinement from the top. And so in the end, it doesn't.
No, when you do these experiments, what's so you're hitting this gold nanorod like 500.
Anywhere from 600 to 680, depending on the plasma resonance of the
Do
system.
you know how hot this gets?
Yeah, that's a very good question. That is something that we don't know. We know it heats up. We know that there's plasmatic heating, and I know it heats up because I can actually see the diffraction pattern expand a little bit during the experiment, which either means it's thermal expansion or more likely the grid is moving in sleeping space. So that's actually something that I really wanted to study. Unfortunately, we hit COVID and then I couldn't keep going. So we have computational experiments. Basically, I did some simulations of the plasmonic thermal heating. The difficulty there, though, is the time scales, right? We're using a pulse laser that's happening at picosecond time scale. We have, you want to know heating more on the seconds time scale. And on top of that, we also have all this, you have to think about the thermal distribution due to the gas environment. So the short answer is no. The long answer is there's a number of ways to do it. There's a lot of ways that I think are very exciting with PM, like measurements of heat, but that's for the future.
You have an estimate what that comes to?
Sure. I don't think it's more. Okay, so not necessarily for this system, but in general, I don't think it's any more than 30 degrees Kelvin personally. But I might be wrong because the other problem is a lot of our measurements are on the macro scale, and we also know that it's probably hotter at the nano scale. So.
Any other questions? Oh, please.
Yeah, so I just had a question about your data sets. So, obviously you're using experimental data, which, as you commented, is very expensive and time consuming to generate. But there's a slew of EEM simulation software out there. Could you comment on, I guess, the pros and cons of experimental data for this versus simulated data for this?
Sure. So I'm actually currently working with a graduate student, basically trying to create simulated HRTM data so that we can actually do this sort of much more systematic study with much better ground truth information. So that I think gets to one of the biggest drawbacks of experimental data, which I don't actually think is the data set size. I think there's a lot of things you can do to really increase your size. But the real problem is you don't have ground truth information. My labels are probably not always going to be correct, especially at the edges of the nanoparticle, which happen to be where we really care about. So that, I think, is the biggest drawback of experimental data. On the other hand, with simulated data, you have much more control. You know the ground truth information. But the difficulty is, how do you ensure that your never trained on simulated data is going to work when it's on experimental data? And so that either means being able to control everything in your simulation, but that, we can control a lot in our simulation, but that doesn't necessarily mean that you create images that look like experimental data. And so it's trying to figure out, what's the simulation fidelity that you need? How accurate do your simulations need to be in order to translate? One really interesting finding that I'll share with you is that the graduate student I work with has, trained these networks on simulated data. And what you see is that where the network peaks in performance when you validate on simulated data is very different from when the network peaks in performance when you validate it on experimental data. And so figuring out that simulation experimental gap is going to be really.
I have a final question, has to do with your machine learning. You always have an operator that's taking a TEM picture that guarantees the particle is going to be in the middle of the pipe. Simulated data, your machine's always going to put one particle in the middle of your picture. Does that have, that seems to me to be a bias that people may not be recognizing.
So I'll say sort of maybe a counter argument. So actually in many of our training data sets, what we do is we actually take a very large scale view and then we randomly sample. And so trying to get rid of that bias, as you said, to make sure that the nanoparticles aren't always in the center of the image. But the other thing that I'll mention is actually with the network architecture we use, it's a convolutional model, which should theoretically be spatially invariant. And so what that means is that if I change my location, if I just shift my nanoparticle region, it needs to give me the same exact effect because mathematically the algorithm itself is spatially invariant. And so, whether or not you actually see that in practice is another story, but I argue that I don't think it's as much of a problem. And also if you do your simulations correctly, you can also make sure that you don't have that bias. And the last thing I will mention is, we've also tested this on, essentially, we train on these small patches of images because of memory constraints, but when testing, you actually don't have these computer memory constraints as much. And so what we can do is we can actually test on images with very different class distributions or like very different nanoparticle densities in the images, and we actually see very similar.
If we have no more questions, it's my great pleasure to present this little gift to Katherine.
Thank you.
Have a comment.
Okay, thanks.
And let's thank Dr. Sytwu again for the very interesting talk. I bring you to the room so you are meet the student and you will have lunch with them.
Okay. Yeah.
What is the gift?
Oh yeah, that's what I was trying to figure out too. It looks like a box of some sort.
Oh, maybe
Um,
some drive with the department logos.
It definitely has the department logo. Yeah, it looks like
Oh,
a
microphone.
wireless charging power bank.
Oh, okay.
That's helpful.